Okay, so welcome to Math 150, Section 1, 2021, Lecture 17. So today I think we're doing more integration, changing coordinate systems and doing different types of integration. So some students have given me some problems that they would like to see, and I will work those in. Are there any other things people want to see, anything from the theory? I'm happy to leave the advanced theory to the lectures and concentrate today on just doing lots of problems. Okay, so the biggest thing to remember when you are doing change of variables is you have to convert correctly. And sadly, depending on what textbook you're using or what subject you're in, you will have slightly different notation in spherical coordinates in the math side than the physics side. I was trained in spherical integration by the physicists first, so I always have to stop and pause and think, how do we do this in math speak? The hardest part is setting up the bounds of integration. If you're given the bounds of integration, the problem is a lot easier. So the real challenge is going to be figuring out what are the bounds. The best way to do that is to draw a picture. And if you have trouble, the best way to do that is to use some of the graphing programs. Mathematical, Wolf and Alpha, which is free online, are great ways to do this and just visually see what's going on. You can also often rotate the images to get a better sense of what is going on. All right, let me just turn this a little bit closer. Okay, there. And so I will start doing some problems, but you have to have Pavlovian responses. So what's a Pavlovian response? Where does this come from? Pavlov, right? When you see En at the end, you'll just basically subtract the En. So Pavlov was a researcher, and he was able to condition dogs so that when they heard a certain noise, I think they had a certain behavior. When you see certain things, you should have instinctive reactions. When you see a product, it's not a bad idea to think logarithms. Logarithms convert products to sums. We are familiar, we are comfortable dealing with sums. Whenever you see x squared plus y squared, what should you be thinking? Circle. And so when you think of circle, that should mean what kind of coordinate system? Polar, spherical, maybe. Spherical would be more of a sphere if you had x squared plus y squared plus z squared. But x squared plus y squared, you should be thinking polar or what else? Cylindrical. So these are things that only depend on the distance from the origin in x, y space. If it only depends on the distance in x, y, z space, think spherical. So one of the problems that was asked was the integral from 0 to 1, integral from 0 to the square root of 1 minus y squared, 1 over 1 plus x squared plus y squared dx. Oh, sorry, I think. This one too? Yes, dx dy. Now, it's not written wrong when I write it like this, but I like to be explicit and write x equals 0, y equals 0. So the first thing is, when you're looking at a problem like this, could I do the x integration directly? And just integrate this directly as 1 over 1 plus x squared. If I gave you 1 over 1 plus x squared dx and asked you to find the antiderivative, this is not beautiful. I'd love to have a 2x upstairs, right? Then I could do like a u substitution. If I had a 2x, I could let u equal 1 plus x squared, du would be 2x dx. And so this would then become the integral of 1 over u du. And you would just have to see how the x bounds change. If x goes from, say, 0 to 4, when x is 0, u is 1. I actually like to be very explicit and write x goes from 0 to 4, u goes from 1 to what? 17. My son's favorite number. And so if I write it like that, we're in good shape. Unfortunately, we don't have that. We have 1 over 1 plus x squared plus y squared. It turns out we can actually handle this. I won't go through all the details, but we talked about this function last time. What function has derivative 1 over 1 plus x squared? Tangent. So, if you would like a real algebra challenge, I can write this as 1 over 1 plus y squared times 1 over 1 plus x squared over 1 plus y squared. And then I would have to rescale x. I would have to send x to a times x, where a is 1 plus y squared square root. And then this is just going to be converted to an integral I can do directly with arctangent, and I have to deal with all the consequences. I don't want to do the details because this is a bad way to go. But knowing the arctangent integration, I could do it that way. The whole point is to hear what is being said. When you see that we have x squared plus y squared down below, what should you be thinking of? You should be thinking r squared. So I've got an x squared plus y squared. Think of that as r squared. Well, let's try to imagine, what is this region going to look like? Y goes from 0 to 1. So here's 0, here's 1. And for a given value of y, x goes from 0, so x starts here, and goes to the square root of 1 minus y squared. So when y equals 1, we just go to there. When y equals 0, what is square root of 1 minus y squared? 1. So when y equals 0, we go all the way to 1. When y is 1, we go all the way to here. And you can just see how far do we go for each one. And this is what the integration is going to look like. If you think about it, the square root of 1 minus y squared, so if the maximum x is the square root of 1 minus y squared, then the maximum value of x is just 1 minus y squared. So the maximum value of x squared plus y squared is 1. Oh, we're just going on a quarter circle. So if I wanted to do this problem in polar coordinates, this is set up beautifully. The region is a quarter circle, nice. It's one of the nicest regions we could have. And the integrand is beautifully set up. So we need to figure out, we start with f of xy, and we want to write this as f of r cosine theta, r sine theta. Well, because x squared plus y squared is just r squared, what is f of r cosine theta, r sine theta? What does that equal? Not 1. 1 divided by 1 plus r squared. So all I do is I replace every x with r cosine theta. I replace every y with r sine theta. I could write this as 1 plus r squared cosine squared theta plus r squared sine squared theta, but I know x squared plus y squared is r squared in polar coordinates. So rather than taking the time to just write that algebraically, I might as well just write x squared plus y squared is r squared. Are people comfortable with this? The next part is the exchange rate. dx dy becomes r dr d theta in polar. So that's how the area element transforms. And now the only thing that's left is I have to change the bounds of integration. Well, I'm integrating over this quarter circle. So I just have to figure out, how do I represent that in polar coordinates? What is the range for r? What is the range for theta? Yes, theta goes from 0 to pi over 2. We always do things in radians, never in degrees, because it's only in radians where the derivative of sine is minus, when the derivative of sine is cosine, and the derivative of cosine is minus sine. Whenever you do differential trigonometry, you have to work in radians. So theta is just going to go from 0 to pi over 4. What's r going to go from? Yes. It is pi over 2. Thank you. What is r going to go to? 0 to 1. Now I have a circle of radius 1. So my angle is going to go like this, and my r is going to go up like that. And now my integral is just going to be the integral, theta goes from 0 to pi half, integral r goes from 0 to 1, 1 over 1 plus r squared, r dr d theta. Yes?
Could you clarify why it's not triangular?
Because we're doing the entire quarter circle. So this is 0 degrees, pi over 4 is to the 45-degree line. Pi half is from all the way up to here. Now what's nice is in polar coordinates, we have a rectangle. And the integrand splits as a product of a function of theta and a product of a function of r. What's the function of r? Yes. R over 1 plus r squared. What's the function of theta? 1. There is no theta dependence. So I can write this as a product of a function of r and a product of a function of theta. This is just the integral. Theta goes from 0 to pi halves of 1 d theta. And then the integral, r goes from 0 to 1 of r dr over 1 plus r squared. What's the first integral going to be? I'm integrating the function 1 from 0 to pi halves. It's just going to be pi halves. I can write it very slowly. The antiderivative of 1 is theta, and I evaluate that at 0 and pi halves. And then I have the integral, r goes from 0 to 1 of r dr over 1 plus r squared. Okay, so we just have to say, well, the first one is going to be pi halves integral r goes from 0 to 1 of 2r dr over 1 plus r squared 1 half. Why am I multiplying by 2 and dividing by 2? Yeah, it's just to make the u substitution a little bit nicer. If you don't do it, it's not wrong. But given that I know what's coming next, you know, we can see we've got a 1 plus r squared, we have an r upstairs. This is exactly what we want to have. And so it'll just make the u substitution a little bit cleaner. So now let's study the integral r goes from 0 to 1 of 2r over 1 plus r squared dr. So let's let u be 1 plus r squared. Du is going to be 2r dr. R goes from 0 to 1. What does u go from? 1 to 2. And so when I do this, this is now the same as the integral u goes from 1 to 2. And now I just have the function 1 over u du. Okay, what function has derivative 1 over u? I'm sorry? The natural log. So this is just the natural log of u evaluated at 1 and 2. Well, the natural log of 1 is 0. So this is just the natural log of 2. And so the answer for our original problem is just going to be pi times the natural log of 2 divided by 4. Whenever you get an answer, you should always ask, is this answer reasonable? Are you surprised that there's a pi? No, we have a quarter circle, so not so surprised. Now, when we look at the function, what's the largest value of the integrand? So what's the largest value of the integrand? 1 over 1 plus x squared plus y squared. Its largest value is 1. Because if x and y equals 0, you get 1. So the integrand is at most 1. What's the smallest value of the integrand? So we have 1 over 1 plus x squared plus y squared on the quarter circle. Where is x squared plus y squared largest? At the end of the circle. So what's the largest value that x squared plus y squared takes on? 1. So the smallest the integrand is going to be 1/2. So we know 1/2 is less than equal to the integrand is less than equal to 1. What is the area of a quarter circle? So if the area of a whole circle is pi, what's the area of a quarter circle? Pi over 4. So then the integral will be less equal to pi over 4. I just use the upper bound of 1 everywhere. And it will be greater than equal to pi over 4 times 1/2. The log of 2 is about 0.7. We know the log of 2 is positive because 2 is greater than 1. And we know it's less than 1 because 2 is less than 8. So this is a number somewhere between 0 and 1. And so since it's less than 1, the upper bound is reasonable. Since it's greater than 0, the lower bound is reasonable. Knowing that it's about 0.69, we actually see that it's very nicely somewhere between 1/2 and 1. So this is not a proof that we haven't made a mistake, but it's a nice way to just quickly check the work we did. Any questions about this part? All right, so I will just try to do a few other problems. So the greatest challenge, as I said, is trying to figure out what the bounds of integration are. If they happen to give it to you, it's not nearly as bad. I find the volume of the region bounded by the plane z equals 1 and the cone z equals r. So one way that you can find volumes of regions is if you can view it as there's a nice surface in the plane and you're going up and down, then the difference from the bottom to the top is going to be your height, and you just integrate that over your whole region. So for instance, the nicest one is, imagine I give you a circle in the unit plane. And I can go up and I can go down. And if I go up to the point square root of 1 minus x squared minus y squared, and I go down to negative square root of 1 minus x squared minus y squared, I'm giving you a sphere. And above each point, I have my upper and my lower. And so I can view the volume of this two different ways. I can integrate over 3 space. I can do an integral over x, y, z, or I can do an integral over x and y, the upper bound of x and y minus the lower bound of x, y. And that would just give me my height. That's essentially just integrating out the z. Either way is fine. If I just care about volume, of course, I might want to just do it directly in spherical coordinates. So for this problem that we were given, we have the plane z equals 1 and the cone z equals r. Yes? Yes.
Then our integrand will be 1.
So in this case, the integrand would be 1. Yes. And that would just be giving us the volume. Now what we could do is we could have something a little bit more interesting. And rather than having 1, we could actually have a density. And we might want to calculate what is the mass. And maybe we'll do that problem next. So here we have the plane z. Yeah. X and y. Oh, u for upper?
No, is that still an x and y?
Over here?
No.
Yeah.
There.
Yeah. Yes.
In the L.
Yes. Oh, sorry. I wrote u and x. Yes, it should be x and y. Yes. And so we're just calculating the height. And so we just want to see what is the difference between the top and the bottom. So if I give you the plane z equals 1, right, that's going to be something like this. And then I'm telling you the cone z equals r. So here, here's x, here's y, here's z coming up. And so I'm going to have some kind of cone like this. What do you think might be a good choice of variables for this? There's more than one possibility. Yes. Cylindrical. Do you think this is a job for spherical? No. Z is playing a very different role than x and y. So I am not thinking spherical. I'm thinking either cylindrical, or if not cylindrical, what else? The sibling of cylindrical. Polar. Because I've got z equals r, which is the square root of x squared plus y squared. So there's a couple of ways of doing this. If I want to find what is the volume of this, one possibility is I could take a circle, and for the circle I could just calculate what is the height below. Or I could take the circle in the xy plane and I go from here all the way up to 1. There's lots of different ways to do this. Do you like the idea of over here coming down? Or do you like the idea of being in the xy plane and going up, and then it takes a while before you enter the region? The more times you do these problems, the more comfort you get, and the more you might actually have a preference. If you don't really have a preference, try one, see how it is. I would actually prefer to have done it the other way. You'll start over here and have a cone like that, which comes to a point at 1. And basically maybe argue that these two have the same volume. And rather than doing z equals r, maybe I can do z equals 1 minus r. And so now when I'm down in the xy plane, when z equals 0, r goes all the way up to 1 for the boundary. And when z rises all the way to 1, then r is 0. Because maybe make the argument that these two are equivalent, and for me, is this a little bit easier to think starting at the point x, y, and going up. So again, the more comfort you have with the shapes, the more times you can make arguments like this and say, this problem is the same as this problem is the same as this problem. I can just do this one. And I can just set up the bounds of integration for this one. And so, do you have a preference between the bottom one here or the one up here? Either one is fine. They're essentially the same. Which one do people want to stay on? The top one? Let's do the top one. So for the top one, we have, I would do, for point x, y over here, we want to figure out what's the range. Okay? And so it's clearly going to be 1, and we go all the way down until we hit over here. For a given value of x and y, does it matter what the angle of that point x, y is from the center line? Or does it only matter how far the point x, y is? When you look at this, does it depend on the angle? No. So it's only going to depend on how far x and y is. So I would do this in polar coordinates. So I would integrate theta goes from 0 to pi, and then r is going to go from 0 to 1. And now what is my height going to be? Well, when I'm over here, the radius is 1, and z equals 1 as well. So what's the height over here? What's the height difference? 0. And if r equals 0, what's the height difference from here all the way down to here? 1. I think the height is actually going to just be 1 minus r. You're trying to think of how far we're going down. Draw it like this. So here's the z-axis. Here's the r-axis. And here's the line z equals r. So what angle is this going to be if this is the line z equals r? This would be what angle? 45 degrees. If we're doing any integration or differentiation, we should be talking in radians. If we're drawing a picture for ourselves, we can definitely do things in degrees. It's 45 degrees. And so when we want to calculate what is the height, we're going like this. We're trying to find what is the height. It starts at 1, and it goes all the way down to the line z equals r. So the height is just 1 minus r. And now, what do I put over here? What's my area element? I'm integrating in polar, so what's my area element? R d theta. Is this a nice integral? Does it split into a theta integral and an r integral? Yeah. So this is just going to be the integral theta goes from 0 to 2 pi of 1 z theta. Integral r goes from 0 to 1 of 1 minus r times r. How should I write 1 minus r times r? Is that excellent? So which transcendentalist did you on? So we forgot it, right? We don't want to keep it as 1 minus r times r because that's a product. By simplifying it like this and writing it as r minus r squared, that's going to be a lot easier to integrate. And so now when we integrate, this is going to just give us theta, evaluated at 0 and 2 pi, times when we integrate this, we will get r squared over 2 minus r cubed over 3 at 0 and 1. So we get 2 pi 1/2 minus 1/3, which is 1/6. So we get 2 pi over 6. Also known as 1/3 pi. Or if you really want to be 1/3 pi times 1. Any idea why I multiplied by 1 at the end? So I will risk asking, did you ever see the following formula in high school? For the volume of a cone is 1/3 base times height. So what is my radius of the base? The radius is 1. So what's the area of the base? Pi. What's the height? 1. The volume of the cone should be 1/3 base times height. 1/3 base times height. So this was a way to just check and see, did we actually get the right answer? And this is one of the advantages of doing this lecture twice. If I do this problem in section 2, I'm not going to be worried, have I made an algebra mistake? But for section 1, it's quite easy. I might have dropped something. You've seen numerous typos already today. But whenever you can check things, it's good to check. Okay. So let's imagine I give you a sphere, and the density. How many of you have taken a science class where they talked about density? What do they normally use for density? Well, should we use rho for density? Absolutely not. Why do we not want to use rho for density? Yeah, we're about to use spherical coordinates, and so I don't want to use rho for density. Do you want to use the letter D for density? Okay, why not? Yeah, we're going to be taking derivatives all over the place, so we can't use rho, we can't use D. What could we use? Any Back to the Future fans? It's a great typo on the line pencil. All right. I need something. We use F. When in doubt, go back to things like that. So we'll use F, X, Y, Z for the density. And let's assume F of X, Y, Z is 4 minus X squared plus Y squared plus Z squared. And we'll have a sphere of radius 2. So I'm basically assuming that it's more dense towards the center and less dense as you get towards the surface. Does that seem reasonable? I think it seems reasonable. Whether or not it depends nicely like this, that's another story. So now I want to set up the integration. So I could go x goes from -1 to 1. And since this is x squared plus y squared plus z squared is 4, I then need to figure out what's the range for y. Well, if z equals 0, then y can be 4 minus square root of x squared. 4 minus x squared square root, so 4 plus. So y goes from minus the square root of 4 minus x squared to 4 minus x squared. And then z goes from negative square root of 4 minus x squared minus y squared to square root of 4 minus x squared minus y squared. F of x, y, z dx, sorry, dz, dy, dx. Yes? Oh, that's right, x should go from what? Negative 2 to 2. Because in almost every example we do, we always have a sphere of radius 1. And I'm deliberately trying not to have a sphere of radius 1. The bounds are not fun to be writing down. Okay? Do we want to do an integration like this in Cartesian coordinates? I want to erase this from the board. This offends me. This should not be written down. Can I erase this now? Has everyone gotten it? We do not want to do that. We want to do this in spherical coordinates. It is hard to hide when to use spherical coordinates. What's the best hint that you might want to use spherical coordinates? You have a sphere. Okay. Whenever you see a sphere, you should be thinking, this is probably spherical coordinates. So I have to give you what's the range for rho, what's the range for theta, what's the range for theta. So for this, what's the range for rho? 0 to 2. I'm going to go over the entire sphere. What's the range for theta? Theta is my spinning the xy plane. What's my range for theta? 0 to pi. And what's my range for phi? 0. And then dx, dy, dz becomes something d rho, d theta, d phi. What is the volume element in spherical coordinates? Yes? It is rho squared sine phi. Well done. I claim the rho squared is the easy part. And the reason is rho is in meters. I need to get to meters cubed. I've got d rho, d theta, d phi. Phi and theta are angles. So I need the rho to make them into lengths. So it's got to be rho squared d rho. The question is, where's the sine of phi coming from? Well, what's nice is sine of phi is always going to be non-negative. If I did the sine of theta or the cosine of theta, that could actually be negative at some points. So that's a good hint that it should be phi and not theta. The other hint is that when we're doing things in spherical coordinates, I come down phi and I have my circle coming out like this. So if this is rho, this is going to be rho cosine phi, this is going to be rho sine phi. So when I'm doing polar coordinates into here, the radius is rho sine phi. So the polar coordinates is r dr d theta. But now the role of r is rho sine phi. And that's another way of just trying to remind you that it should be rho sine phi, not rho cosine, not rho cosine phi or sine theta or cosine theta. This is going to be non-negative, but this is just something that needs to be memorized. Okay, so now we need to do the integration. So I'm going to integrate p goes from 0 to pi, integral theta goes from 0 to 2 pi, integral rho goes from 0 to 2. And then what is my function f of x, y, z when I replace x, y, and z with all the different stuff? And you have to remember what is x, what is y, what is z. So if I start writing down, you would get x is going to be rho sine phi, cosine theta, blah, and all the other crap. But I claim I don't need that. What does 4 minus x squared plus y squared plus z squared look like in spherical coordinates? It's just, I'm sorry?
4
4 minus rho squared. Right? And then we have rho squared sine of phi, the rho, d theta, d phi. As you start to get more comfortable with the integrands and the integration, you can start skipping some steps. Of the 3 integrals, one integral is going to be really nice. What's the integral that's really nice? Is it the rho, the theta, or the phi integral? The theta. There is no theta dependence in the integration, in the integrand. So what is the theta integral going to give you? 2 pi. It's just 1 integrated from 0 to 2 pi. So as you start to become more comfortable, rather than writing the integral theta goes from 0 to 2 pi of 1 d theta with all this other stuff, you can just say, you know, I don't need to do that. I can just say the theta integration gives me a 2 pi. If you're not comfortable doing that, by all means, take the extra step. And so now I have my phi integration. It's going to be the integral phi goes from 0 to 2 pi of sine of phi and phi. And then the integral rho goes from 0 to 2. How should I write the rho integration? Rho squared minus rho to the 4th. And that avoids having to use the product rule. All right, so now we just get 2 pi. What function has derivative sine of phi? Oh, whoops. This should be only going up to pi, not to 2 pi. What function has derivative sine? Minus cosine. So there's 2 ways to do this. I can write it as minus cosine evaluated pi and 0, or cosine and then switch the order of integration. I'll just do it this way. Minus cosine of phi at 0 and pi. And then here for this piece, it's going to be 4/3 rho cubed minus 1/5 rho to the 5th at 0 and 2. All right, when I plug in pi, I'm going to get negative cosine of pi, which is going to be plus 1. And I subtract off negative cosine of 0, so I'm subtracting off the negative 1, so that's going to be 2. So I'm going to get 2 pi times 2. And then over here, when I put in 2, I'm going to get 8 times 4 is 32 over 3, so it's 32 over 3 minus 32 over 5. Could I simplify this further? Yes. It's nice that they both have 32s over there. So it's going to be, 1/3 minus 1/5, which is going to be 2/15. So 32, 64, 128, 256. So I believe it's 256 pi divided by 15, if I've done the algebra correctly. Okay. So I will do different problems in section 1, just again to give you as many different ones to look at as possible. I'm going to end, since we don't have that much time, with one of my favorite integrations by symmetry arguments. So there's frequently more than one way to do a problem. And depending on how you see it, you could have a tremendous amount of algebra for a little bit. So I want to integrate from 0 to pi over 4 of, I'll do pi over 4. Cosine squared of theta d theta. So the problem is I need a function whose derivative is cosine squared theta like integrate. This is not so pleasant. So there are some trig identities you can do. And so you can try to play some games using trig identities. So for instance, cosine of 2 theta is cosine squared theta minus sine squared theta. Well, that's the same as 2 cosine squared theta minus 1. So cosine squared of theta is going to be 1/2 cosine 2 theta plus 1/2. And so if I write it like this, I can now actually integrate this. What function has derivative cosine 2 theta? So what function would have derivative cosine 2 theta? 1/2 of sine of 2 theta. The derivative of sine of 2 theta would be cosine 2 theta times the derivative of 2 theta, which would be an extra 2. So it would be 1/4 the sine of 2 theta plus theta over 2. And if I take the derivative of that, I will get cosine 2 theta. I mean, I'll get cosine squared theta. And so I could then use this and evaluate this at 0. There's a nicer way to do this. When I'm integrating cosine squared from 0 to pi, do you agree that that's just the same as 1/2 the integral from 0 to pi of cosine squared theta to theta? Does that seem reasonable? And is that then the same as 1/4 the integral from 0 to 2 pi of cosine squared theta to theta? And what's nice is I'm squaring cosine, so I don't have to worry about the negatives. But the integral of cosine squared over a whole period is the same as the integral of sine squared over a whole period, because sine and cosine just differ by a phase shift. So this would be the same as 1/8 the integral from 0 to 2 pi of cosine squared theta plus sine squared of theta. What do we know about cosine squared theta plus sine squared theta? It's 1. So this is the same as 1/8 the integral from 0 to 2 pi of just 1 d theta. What is that integral equal to? Just to go to 2 pi, so we get 2 pi over 8, also known as pi over 4. We were able to evaluate this without knowing the antiderivative. And this is a technique that's worth having in your wheelhouse. That sometimes, if I give you an integral over a nice region, you can actually find the integral without knowing the antiderivative. In general, we like to use the fundamental theorem of calculus. We like to say the area under the curve is the antiderivative of b minus the antiderivative at a. To do that, you need to know the antiderivative. There are some functions where it is hard to find the antiderivative. We can do it, and by being a little bit clever with our trig identities, we were able to get that. As another nice example, let's say f of x equals the natural log of x. What function has derivative natural log? We know the derivative of the natural log is 1 over x. But can you give me a function whose derivative is natural log of x? There is a function. So I'll make that an extra credit problem. You find the function whose derivative is natural log of x. And if you know that, then you can do the integration very easily. But if you don't know the antiderivative, this becomes very hard. So for some problems, when there is symmetry up the wazoo, the technical term, then you don't have to know the antiderivative. And I can just say, this integral is the same as this integral is the same as this integral is the same as this integral. At some point, you have to do something. So the goal is you keep doing this until you reach a point where you have something that you can do. right, so this is a good place to stop.